All right? And that is all we're going to say about this algorithm. And if you loved it, then what you should do is you come to 3101. And if you didn't understand it and you're thinking, how the hell am I going to handle this on the exam? It won't be on the exam. All right? All right, so what will be on the exam is I did like, we put on the homework assignment a question about the look-ahead 1 grammar and how that parses. I think that's a great algorithm that you should all be up for. I think this is a dynamic programming algorithm, and after taking a couple weeks of dynamic programming, I find about half the students can write a dynamic programming algorithm, and about half the students fail. Right? So I don't expect you to be able to do it right now. All right? But maybe it gave you some flavor, and it'll help you when you'll be processing it in your sleep. In fact, you know what? Tonight, you're all supposed to have scary dreams, right? Because it's Halloween. Happy Halloween, everybody. And you can dream about dynamic programming. All right? All right, so how are we doing for time? We go from 4 to 5:30, so we still have lots of time. Excellent. So, any questions about what we've done so far?
Yeah, what just happened?
What just happened with dynamic programming?
Oh, yeah.
It was a nightmare.
So, Professor, just to confirm, everything that said dynamic programming, all the slides that had the word dynamic programming in it, it's not in the exam.
You're not going to make me say that twice, are you?
It's a good news, right?
It's being recorded, so you can listen, but you didn't hear me say that. All right, so context-sensitive grammars, just to fill out the whole topic of grammars. Chomsky, who invented all this stuff, also invented context-sensitive grammars. So context-free grammar has a rule that whenever you see a C, it doesn't matter how the C is appearing in the rest of the string. The context doesn't matter. You can replace it with an ABC, right? So that's context-free grammar. If you have a context-sensitive grammar, then the rule will be, say, whenever you see a capital C with the D, little d before it and little c after it, then you can replace this whole thing with that. And that allows much more power in our grammar. So here's an example, and it says you can replace the BCC with the ABCC, right? But if it appears in a different context, then you're not allowed to replace it, right? Does that make sense? And context matters. And so if you look in the books, sometimes context-sensitive grammars, they allow shortening rules, and sometimes they don't allow shortening rules. If you don't have a shortening rule, then the string that you're parsing keeps getting longer and longer. But we're gonna allow shortening rules as well, and then that gives us even more power. And in fact, what we have as much power as doing a Turing machine. All right. So what we're going to prove now is what we're going to show is going to give you an example of a context-sensitive grammar, and then we're going to show how it's as powerful as a Turing machine. And I just remembered something I wrote on the board last time, so I should make a new slide and write it on the board now. So what we're trying to prove is that, right, if we want to prove that for every string, if the string is in the language, then the grammar generates it. And if it's not in the language, So here, this is your grammar can generate it. And of course, this is a non-deterministic grammar, right? You have a fairy godmother telling you which rules to apply. So if the string is in the language, then you can start from the start state, and you can use non-deterministic rules, and you can generate alpha. Yes. Completeness and soundness or something, if you want to do proof systems here. Right? It's funny, I know. That's another thing we can have nightmares about tonight, right? All right? So if it's in the language, then it can be generated from our grammar. And if it's not in the language, it can't be. All right? So let's see if I can remember to make that slide. All right, so what we're going to do now is you give me a Turing machine, and I'm going to give you a context-free grammar. Context-free grammar. No, that's supposed to be an S here. Another typo. Everybody marking all those typos that I'm going to have to remember? Context-sensitive grammar, such that what the grammar can generate is equal to what the Turing machine accepts. Alrighty, so we're going to be simulating this Turing machine. Alright, so we have to somehow write down what the Turing machine is doing. And so we're going to encode it as a string of terminals and non-terminals. So we start with just the tape, and we mark the beginning and end of the tape. So here's the contents of the tape, and we mark the beginning and the end of the tape like that. And then we have to have marked what state the thing is in, and for every state, we're going to have a non-terminal capital Q representing that state. And we have to mark the head location, right? And how do we mark the head location? Well, we just put the state where this means this is the contents of the tape, and the head is on this character, the character past the Q, and we're in state QI. All right, and so in fact, I have a slide in a minute which shows that this is the notation Sipser uses in his book anyway. So if any of you are reading, actually, that's a good question. Are any of you reading the books?
No.
Is anybody reading it and finding it? You guys are reading it. Are you finding it useful? We got two usefuls back there. All right, so which one are you reading? Sipser? Excellent. All right, people understand this notation? This is the notation Sipser uses. Yes?
How is spelling done on a tape?
That question hasn't gotten up yet here, so why don't you wait until we have that question. You're kind of jumping pages and pages ahead. I'm just saying, how does this relate to the Turing machine state? All right, let's keep questions on the slide in question. Your question on the slide in question?
The head location.
Yes?
Yeah, so QI. You're saying that QI is what the head is looking at to the right of it.
Yeah, the guy to the right is
So therefore, it's going to start actually before the 1 and end before that final 0.
yeah, if it's looking at the 1, it'll be here.
And when it finishes, it's going to look...
If it's looking at the first blank, it'll be here. Right? All right. So now, let's come up with some grammar rules. So suppose that the Turing machine is in this configuration, and we have some delta rule, and the delta rule says, hey, I'm in state QI, I see a 1, what do I do? Well, here the rule is saying, if I'm in state QI and I see a 1, what do I do? Well, the rule might say, write QJ, all right, so we're gonna change that to a QJ. It says change the 1 into a C, right? So you change the 1 into a C, and then it says move the head, so you swap the C with the Q. Everybody see how what we did is we went from this to this.
What's the swap?
The swap, this C that used to be a 1 is swapping with the Q, because now we're looking at this one.
Swap in there.
What?
I mean the swap in there. Like, where's that swap happening in there?
The head moved. Let's do it again. All right? We observe that we're in QI and we're looking at a 1. Right? So what do? We turn from QI to QJ. We change the 1 that we're looking at into a C. And then we move our head right, which swaps the C and the Q. Right? So what's the rule? The rule says you can change QI1 to being CQJ. Right? That's the context sensitive rule. You see how it's just mimicking the movement of the head of the. We change states and we move the head. Everybody kind of follow that? So now it's a little harder when we move left. So if we move left, then we change to J. We write the 1 turns into a C, and now the